Hello? Yes. Okay. Hello? Yes, now it works. Okay. Okay, the idea was that I studied the issues I had in the two first days. We discussed very much the voltage you have here, and then also the reactive in-feed you got from the grid. So I made some small examples. I made them yesterday. Uh, what you will see here is very much this Rx quota that I'm talked about a lot of time. The first question was, what was it? If we want to decrease the voltage, what is the most important to change the wind power production or have reactive change in the wind power plant? And then what you can see is that the total here, in this point, sum of R is equal to 4.0.4, so it's 1.6. Sum of X is equal to 6 times 0.4, so it's 2.4. So this means that the X is larger than the R. And if the X is larger than the R, this means that Q has more impact than P. Then it's also like this, that P is, of course, to change to P means in reality that you are changing something that you can get money from, because the P is producing power, while reactive power is something that you probably have here. So on the other hand, this is not exactly trivial. What is the most important thing? Because the question is more an economic, from the economic point of view, it's of course always better to do something in the Q than to decrease the wind power production. But if you compare megawatt with megavar, then you, because in this formula, then of course it means that it's better to change the Q than the R. So it's in reality better to change the Q, and it's very much, it has a bigger impact to change the Q also with 1 megavar instead of changing the active power with 1 megawatt here. Why is power grid fed with a higher amount of reactive power? So what you do here is that you are sending in this case, you are sending in here, I think it was here, 2.48. And then you are only consuming 0.5 there. Here you are not doing anything. And the reason is, of course, that you have an X here, which is creating reactive losses, and you have an X here, you're creating losses, and you have an X here, and they are creating losses. So what is sent in here is consumed here, 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 and here. That's why this one becomes bigger. And these kind of reactive internal losses that you have in the system is, of course, important when you are discussing voltage control and this kind of thing also. So that was B. C. Is it possible to use reactive power to both keep, because this is an issue that is discussed nowadays, that this is, of course, has to be supplied from somewhere. And the question is, because that is also what I discussed, that in the future system, when you have more solar and wind power out in the distribution grid, you want still to keep the voltage here. And here you suddenly start to consume a lot of reactive power. The question is to handle that. Can you keep down that to zero? Because that is, for example, the rule in Sweden, that the distribution grid should not consume any reactive power from the transmission grid. So this is, let's say in Sweden, this had not been acceptable. Okay, it's very small levels, but anyhow, that was the idea, that can you, using the reactive power here in order to control this one. In this case, this is not possible, because what you should do is consume more reactive power here, because the voltage is already 1.1. I used my small program to check, to make the calculations. The voltage is already here 1.1, what was it? 1.102 per unit. So And we have said that the voltage should be within plus minus 10%, so you should decrease the voltage, try to decrease the voltage here. If you want to decrease the voltage here, you should consume reactive power. If you consume reactive power there, then of course you will send in more reactive power here. So it's not possible to take that one down to 0, because then you should produce reactive power. And if you produce reactive power here, you will get even higher voltages, which is not possible. So in this case, so in reality, if this is too high, you have to compensate it here with capacitors or something if you don't accept this one. It's not possible to compensate that out here since you already have too high voltages. That, oh, is it possible? No, that was 1C. And then we change to cable. What happens then? When we change to cable, what is happening is that, I mean, in an overhead line, you have, if just take the basics, you can read parameters, but it's good, of course, to have something. If in a transmission line, you have these 3 phases, and then you have the current going around in a circle like this. And currents that are going around in circles, if it's AC currents, they create an inductance. In reality, if you have a big circle, you create a big inductance. If you have a small circle, you create a small inductance, because it's the magnetic flux that is changing. And in cable, in reality, you're having them much closer. So that's why the reactance go down when you have cable. And that is very important, because here you have a huge amount of overhead lines. We had it earlier in Sweden also, by cablifying more and more. And what is happening when you cablify is that you reduce the resistance in the system. And that impact on what is how this you get more capacitance when you are cablifying, because the lines are closer, so you get higher capacitance. Hello, it sounds a bit so in this case, the next case, when I have the case happened, I reduced this one. It's not any longer 0.4. Is the no, it's the reactance. There you still should have 0.4, and then what is happening is that here you instead get 0.1. So then you get 0.4 plus 0.4 plus 0.1. So then the sum of the x will now instead 1.2. So now you have a different system. Now the resistance is in reality larger than the reactance, but that is not exactly what I asked for here. What I asked for is, what is it? Why did the voltage increase? Because the voltage becomes 1.12. So the voltage increased when you change to a cable. Why? The reason is that you can see this way. If you look on this system, you are sending P in that direction, and you are sending Q in that direction. Here you have the voltage difference is the R times P plus X times Q. This is increasing the voltage. R times P is increasing the voltage, while X times Q is decreasing the voltage. So here you have an increase, here you have a decrease, because Q is going in the other direction. Since Q is going in the other direction, then the question is, how much is the impact from the voltage decrease? How much does that decrease the voltage? It depends on the size of the X. Now X is decreasing because you change to a cable. So when you change to a cable, the impact from the reduction of this one is decreasing. If you have consumption, this is good, of course, because then you get a stronger grid. You don't get so much decrease because of the reactance. But if you have production, as we have here, then it's not the same thing, because you are consuming power, and the consuming power is good for the voltage decrease. But that here, so the the decreasing impact decreases, so to say, to make it complicated. So you don't decrease the voltage so much with the Q, and that is the reason why you get this. Of course, I mean, I think, as you see in all my questions, it's important, I try to get some kind of understanding instead of calculations. You can always do. You can just put it in load flow and then you get an explanation. But I think it's very good to have this feeling also, okay, perhaps we should change the cables. To just have a feeling about what will happen if we do this. And this is just some basic thing about that. Can we now use wind power, reactive power? No, it's even worse now, because you have an even higher voltage and you are still consuming a lot of reactive power. So it's consume more reactive power, because now you have to consume even more reactive power in order to decrease the voltage. And you will see the system, then you will even more, let's say, increase the consumption. That was part 1. Part 2, why becomes inertia? Why inertia becomes, okay, English, anyhow. Why becomes inertia an important challenge? The reason is this extremely fast response. Exactly when something happens in the system, the initial balancing in the system is the inertia. And that comes in conventional power system, in all power system, it comes from synchronous machines, mainly. Then you have a small contribution asynchronous induction machines, also from motors. You get a physical response initially. On the other hand, if you have a huge amount of solar and wind power, if you come up to, let's say, 70 or 80% of the power system, if you have a huge system, you still have a huge amount of inertia in the system. On the other hand, if you have small systems, then of course, and you take away a load of, you replace the synchronous machines with HVDC or some kind of power converters of some kind, then you reduce the amount of synchronous machines, and then you can get very fast, rapid changes. As I had this parallel, you are braking a bike and your weight is 0, then of course you will stop the bike immediately. Can wind power contribute? Yes, wind power is a bit better than solar. In wind power, you have an inertia. Then, of course, if you have the conventional type, the star type, where you have an induction machine directly connected to the grid, then you have some inertia just because of the synchronous machine, but that is very small. You have a small contribution from, because you have the slip, but you don't, so it's not so big. But the modern type of wind turbines normally have a converter. Then you could, of course, measure the frequency, but remember that, so this is not exactly inertia. Inertia is that exactly when you have a problem in the system, you disconnect a plant or something, you increase demand. Exactly when that happens, you get contribution from the inertia. It's when you have used some inertia that the frequency go down, so-called, and what you can do is, of course, measure the frequency, do something. Remember that if you measure that the frequency had gone down, that means physically that you have used some inertia. So you cannot say that we can use, so all this kind of so-called synthetic inertia is based on that you have some inertia in the system which is used, so the frequency is decreasing. I can say that exactly about now. This is a really hot topic. We are discussing internally with companies like ABB and so on, because that have happened. I mean, there is a discussion now that the system operators will require inertia from, for example, system. And then the question is that how to make these fundamental calculations. Do we really have synthetic inertia? You have to measure the frequency, but if there is no inertia, there is no frequency to measure. Okay, this is really fundamental. Can you have an RMS modeling at all in the system if you don't have an inertia? But then we are coming down to really small amount of inertia. But at least what you can with wind power is that you can have extremely fast primary control, if you call it like. And primary control is normally you measure, okay, the frequency has gone down, I do something. But here you can, it has to just decrease a little, and then you can do something fast. So I don't think you can answer this answer in 3 lines. It took me 10 lines at least to do. Anyhow. So wind power can do something, and then you come into the other part, and then both wind power and solar power. What you normally do in solar and wind power is that you keep as much production as possible. You have solar power, MPPT, that is getting to maximize the amount of power. So always, because why should you not get as much as possible? And then, of course, what you always can do is that, okay, too high frequency, we decrease. So 50% of the primary control, of course, you can do. If it's too high frequency, we just curtail the wind power or solar power. So you cannot say that you cannot do, if you're on a maximum, is that you cannot increase, of course. But if you're on the maximum, you can always decrease. So 50% of the frequency problems you can manage. So you can partly participate. And then you have the other issue, which is coming more and more, which you have more of that technology today, and that is that if this is the maximum, you can, of course, operate it slightly lower. But then the question is, why should you? Why shouldn't I use all the energy in the wind? Why shouldn't I use all the energy in the solar? I mean, it's more or less stupid to not use everything you can. But in extreme situation, or if you have an extremely surplus, you can decrease. And then if you are decreasing the production in solar and wind power, then of course you can have primary control in both directions. If you're on the maximum, you can only decrease. If you are lower than maximum, you can go in both directions. I think that was all. So if you have not answered it, now we have the answer anyhow. And if you have not answered this, then you have learned more, because you learn by your mistakes. So if you don't make mistakes, you don't learn anything. Okay, thank you.